In our final application of thinking about spectral theory, I'm going to think about computing spectra of operators. And the method we're going to use here is based on the Fourier transform, and we call it the Floquet-Fourier-Hill method. So computing spectra of operators is often a really important thing to be doing because the operator itself, for linear problems, contains all the information you need about a given problem. In other words, encapsulates the physics very nicely. So we're going to think about problems of this form. Kind of looks like a Sturm-Liouville problem, but we really want to compute generic spectra of some operator, linear operators. Of course, this is restricted to linear problems, but oftentimes, unless L is simple, we can't write down analytic solutions, but we would still like to compute what the spectra looks like. Because really the spectra, the eigenvalues and eigenvectors, tell you everything about the problem itself, and they also set up the basis functions you're using to expand your system in. So you can use these basis functions for solving PDEs, characterizing PDEs. So computing spectra is really an important exercise in general, where this operator L, by the way, is just here. It's a differential operator that has non-constant coefficients. Oftentimes, for a restricted class here, especially the Sturm-Liouville type equations, we can actually analytically write down what the spectra look like. But generically, if I give you something and you still want to compute what the spectra looks like and what the modes look like, in other words, the eigenfunction expansion, it's a very difficult thing to do, and you have to rely on computing to do it. Finite differences can work, but they're not nearly as accurate as spectral methods. And so we want to start implementing spectral methods here for computing our spectra itself. So the method is based on this observation that any function f of kx, in other words, any of these f of 0, f1, fm, can all be expanded in a Fourier expansion itself. So we're going to work on a domain, 2π periodic domain, and there's the Fourier transform pair of this. And so in a discrete form, or at least this is a discrete form here, where all the coefficients here, the loading coefficients, are just a projection of the function against the Fourier modes. Okay? So you have to do this integral, and this is what an FFT does for you, to get actually the coefficients here. So you can take any one of those coefficients here, or any one of these functions here, f0, f1, that sit in front of the derivative terms. F1 sits in front of the first derivative, f2 into the second derivative, and so forth. And we could expand each one of those functions as a set of Fourier modes. That's the first step, is that observation. The second step is the observation that comes from Floquet theory, which says all bounded solution of this form here, or of this form here, where it's some phase change variable, or it's some exponential with mu times a function phi of x, where phi of x itself is periodic. So this is for periodic problems, periodic extended problems, which is exactly what we're doing here in computing the spectra, and mu is in an interval 0 to 2π over L. And so in Floquet theory, the e to the I mu x is called the Floquet multiplier, and the actual exponent itself in there is the Floquet exponent. And so this, if you work in solid state physics, this would go under block modes or block structures. And so that's where another name for this. They're the ones that consider it often, because in a lot of material properties you have periodic structures across your material, so you often need this Floquet theory. Or you can look at Floquet theory in terms of determining the stability of periodic orbits, for instance. So in either case, Floquet theory is going to play a role here, because we're going to expand everything into Fourier modes, which means we're kind of assuming kind of periodicity assumptions around this expansion. So some things that we want to do here. We're going to do a Fourier expansion now. So we're going to take this omega x. We have here our Floquet multiplier, but then now we take this phi of x, which is periodic, and since it's periodic, we do a Fourier expansion of it. Now once we've done this Fourier expansion, remember, and we can kind of actually, now that we've done this expansion, we can bring in the Floquet exponent inside. That's what we have here. And then we can actually notice that this coefficient is here, is an inner product for the function originally times this here. So this is like our projection into that Fourier space of the function. Okay? So within that context, or within these Fourier expansions, we can now come back to compute this linear operator by expanding each one of the coefficients in terms of this representation with Floquet exponents. And here's what the representation is. You have the mu that's here 2 pi over ml, and then here is your coefficients f of x. And this here gives me now, if I've discretized this eigenvalue problem, here is the discretization of the eigenvalue problem as a function parameterized by mu in terms of these phi hats. Okay? And if you manipulate this a little bit, this is what this operator looks like. This is what the L operator looks like after some manipulation. It is the coefficients of that projection times this term here raised to the kth power. This comes from differentiation, right? So every time you take a derivative, you drop down the power here, and that's what this is here. So this gives us a representation of that operator now in this Floquet Fourier space, okay? And Hill's equation is just simply looking at equations in this form of periodic coefficients. And that's exactly what actually the context we're looking at. His here is these functions are periodic. The f of 0, f of 1, and so forth are periodic on some with period of length L. So we could do all of this expansion of the Hill equation, that's where the Hill comes in, using Fourier modes and using Floquet theory, so Floquet Fourier-Hill method. So let's take an example of this projection and building this out in practice. Here's two operators. They come up out of nonlinear Schrodinger equation as linearizations of the Schrodinger equation. And one of them is this operator here. The second is this operator here. So it's non-constant coefficient with a hyperbolic secant squared here, a 6 hyperbolic secant squared here. And so what we want to do here is start looking at the terms. So f of 0 is the term in front of the constant, and that's this term here. So here's the term in front of the constant, here's the term in front of the constant. And what we're going to do, we're going to have to do a Fourier expansion of both of those functions. There is no term, there's no first derivative, so f1 is 0, and the term in front of f2 is both -1 here. There's no f3, f4, and so forth. Okay? And so the first thing we need to do is compute Fourier transforms of these and stack this up. So let's go ahead and do this. Let's define hyperbolic secant. I'm going to pick a domain inside 40, chop it up into 200 points, and my tolerance, in other words, the actually I'm going to go after is 10 to the -8. So here's how this works. So what we're going to do is we're going to come here and compute using our Python. We're going to compute the integral of the projection of the secant onto the Fourier mode basis. And that's what this is doing here for the different cosine modes, cosines 0x, 1x, 2x, against hyperbolic secant, and we've picked an accuracy tolerance of 10 to the -8 to get those numbers out. And what that gives us is all the coefficients in front of the expansion of the Fourier mode expansion of the projection of the hyperbolic secant squared on a Fourier mode basis. Okay? Once I have this, I can now arrange, I'm ready to build my linear operator because now I had an explicit construction of how to build in these A of n's using what I have here, right, the A of n coefficients. I have all the coefficients here, and so now I can build out a matrix and populate it with the different A of n's that I have computed from here. So here they are here, A of j, j minus 1, and so now I'm putting in along my matrix, my linearized matrix, where those coefficients are in the operator itself. And this is just, all those A's are coming from the F0x expansion and loading this up. And so once I've got that, I can actually build my linear operator. Here it is. So it's got the two derivatives in x, right, plus the constant term, and where I've built in the A of matrix. And then once I have that, I'm just going to do an eigenvalue solver. Because if you come back, let me walk back a few slides just to show it. This is what I'm computing right here. This is the operator. So I can compute this for the f of 0, and I know what it is for the f of 2 because it's just -1. And so once I have these, I can actually construct that operator and then do an eig solve from there. And I can either do the eigs for the first operator or the second operator, and here's the results of those. So what you're looking at here is the spectra of these operators. Here's the L plus spectra. There's an eigenvalue right here, one here, and then I have a continuous set of modes there. L minus has one mode here. The rest of the spectra is here. This is also a continuous spectra. And if I look at these discrete modes, so if I look at the discrete mode here for the L plus L minus, this is the first mode whose eigenvalue is negative 3.001. So the actual eigenvalue is exactly at negative 3. So you're within 10 to the minus 4. Then there's a zero mode, which is this one here. This is what it looks like. It's hyperbolic secant tanh. And this mode is essentially you've got it to within 10 to the minus 3 digits. And then the zero mode here, it's accurate to 10 to the minus 5th. So these are the modal structures that you get out of this. This is the most accurate computation of the spectra possible. If you do finite differences to get this kind of accuracy, I didn't use very many points here. You need significantly more data points because you're converging algebraically to the solution versus this is exponentially to the solution. So this is why you might want to use Fourier modes again, as you're leveraging the properties of exponential convergence versus polynomial convergence to the solution. Here's another problem that we want to do. This is the Matthews equation. It's kind of a famous problem out of differential equations where you have some oscillation here with parameterized by omega and strength Q. And so again, you can take this operator and find that F naught is actually 2Q cosine omega x. In other words, look at that, you have explicitly cosines here, which is two frequencies, right? E to the I omega x and E to the minus I omega x. I mean, same frequency, but complex conjugate pairs. F1 is 0 and F2 is negative 1. Again, you can define, and what we're going to do now is scan across Q values, and we're also going to do this for different mu's that I'll show you. Number of points, the number of cuts that we have, and frequencies that we want to scan. Or the frequency itself is going to be 2. That omega is going to be 2. And so here again is the code. We have to project the data onto the Fourier coefficients. Okay, so the F naught gets projected onto the Fourier modes that we're using. And once we have those, we can now construct our linear operator and use an eigs here at the end. In other words, we're computing the eigenvalue structure, the spectra of this, in this Fourier domain using Floquet theory and a Fourier representation. And here's what this looks like as I scan across the omegas. Okay, these are these instability tongues. So if you've ever studied Matthews equations, you'll see pictures of this, and often we'll do asymptotics of this, and we can kind of get some idea of what happens here, down here, near the bottom of this, right, where we have Q being close to 0. That's our asymptotic expansion. But here we can get the whole thing numerically very rapidly, and this is beyond sort of your ability to really do analytically, and you do this not only extremely accurately, but extremely cheaply, computationally, using these computational techniques. And it gives you the full operator spectra, which is a very difficult thing to typically get, but you can do this really easily with these computational tools. And so it's another important piece of operators, and operator learning is something that people do quite a bit of in PDE theory. And again, this is using spectral methods. Go right after this spectral representation eigenvalue problem that is at the heart of understanding your PDE or your evolving system. Because once you have your spectra and eigenfunctions, you know everything about your system. And that's kind of like, I think that's the basic idea of having eigenvalue and eigenvector decompositions. And here, it allows you to get them in a very accurate way, very cheaply, using this Floquet-Fourier-Hill method. So we'll end there, and that's sort of the end also of our spectral methods. And you can see that spectral methods are really powerful techniques that are computationally efficient, very accurate, and can be used for a wide variety of applications.